Hello, everyone. Today, I would like to talk about my work on wire functions from NP-complete problem. And this is joint with Professor Rafael at Cornell Tech. So today, we're going to focus on wire functions, which is a genius notion proposed by Diffie-Hellma in '76, which is roughly 40 years ago. So a function f is one way if it's easy to compute and hard to inverse. And as usual, by easy, we mean it can be done in point of time. By hard, we mean no PPT can inverse this function. So it should be easy to go from the input x to f of x, but it should be hard to go from f of x back to the input x. And I want to mention a famous example of wire function candidate. It's based on the factoring function, in which we use the input x to pick two large random primes p and q, and we simply output p times q. And it's easy to see that this function is easy to compute, just multiplying two numbers. And if you believe that the factoring function is hard, then this function is also hard to invert. And let us introduce the formal definition of one function. We say that f is one way if for every PPTA on a random input x, that's y equals f of x, and the probability that the adversary a on input y finds an arbitrary pre-image of f of x is at most a negligible amount. We know that one-way function is the is a very, very important notion in cryptography, and it is both necessary and sufficient for a branch private key crypto primitives. And it was amazing that, say, Diffie-Hellma could discover or could have this provision 40 years ago that this minimal object unit for cryptography is this cute function that, say, is easy to compute but hard to invert. And we know when a function is characterizes the existence of a private key encryption, pseudorandom generators, digital signatures, authentication schemes, pseudorandom functions, commitment schemes, coin tossing schemes, zero-knowledge proofs, and so on. Whether one-way function exists is the most important problem in cryptography. And also observed by Diffie-Hellma, the existence of one function implies NP is not equal to P. To see this, if we assume NP equals P, then we can solve NP search problem, and inverting a function would not be hard. So, as proposed by Diffie-Hellma, the holy grail of cryptography would be to base the existence of one function on the worst case hardness of NP. And there are many results towards proving this holy grail, but most of them are in some sense negative results. And we want to mention that here those separation results are in some sense partial black box. So they either only consider restricted type of black box reduction, or they only consider restricted type of one functions. So to base one function on NP is not equal to P is still open. So in the absence of the holy grail, Liu and past 20 showed a characterization of one function. And they showed that one functions exist if and only if the so-called T-time bounded Kolmogorov complexity problem is mildly hard on average. As we will see later on, the notion of Kolmogorov complexity is really like a nature classical notion and has been studied in the 60s. But now let me skip its definition. So in some sense, this result tells us where in the world of complexity theory one function and the cryptography should and go in. And now the question is, well, how about the holy grail? So how about we kind of zooming out this small picture, and we observe that there are two additional steps that we have to prove if we want to achieve the holy grail. So the first step is to show that this problem MKTP is NP complete, and the second step is to give a worst case to average case reduction for this particular problem. And we observe that these two steps, these two red arrows, are in fact also necessary for achieving Holy Grail. To see why this is the case, so first we show that the first red arrow is necessary. Assume that a function can be based on NP is not equal to P, and assume that NP is not equal to P. Then we have one function. Then we have this problem is average case hard, and therefore it's worst case hard. So we showed the NP completeness of MKTP. And to show that the second red arrow must also hold, observe that if MKTP is not in P, then NP is not equal to P, and then we have one function, then this problem is average case hard. So therefore, this is the worst case to average case reduction for this problem. So it seems that, well, we have to prove these two red arrows. So how's the program? How's the progress? Unfortunately, for the first red arrow, NP completeness of MKTP is a long-standing open problem in algorithmic information theorem. And as for the second red arrow, we have some good news. And very elegant work by Hirala proved a worst case to average case reduction for MKTP, but he only obtained the so-called errorless average case hardness, which is slightly weaker than what we need, but we still have something there. So it's kind of weird that here that the NP completeness result becomes like a harder one, and we seem to have some hope for this worst case to average case reduction. So now the question is, can we replace the first red arrow by a black categorization? So the question is, can we base one functions on average case hardness of a NP complete language? And so this basically will bring us kind of one step closer to our Holy Grail. And this question was raised by a very elegant paper, Allen et al., but unfortunately it was not solved. And we want to mention here that this L should be something useful, or in other words, nature. And here is a very artificial construction of L. Just consider embedding set instances into the MKTP problem. And unfortunately, I don't have enough time to go through this construction, but I do want to mention here that, well, there's no lesson we can learn from this artificial language. And in some sense, it's not an appropriate bridge connecting the worst case hardness and average case hardness. So ideally, we want some language which should be natural and useful, sitting here and tells us something about worst case to average case reduction. And let's, for example, MKTP would be a great choice here. So in some sense, our main theorem identified such a language which can sit here as the language L. Before introducing our main theorem, I want to also recall that there is a long history of basing cryptography on average case hardness of NP complete problems. And the NP complete problem they choose, which is also very nature, is the subset sum problem. However, we know that the average case of subset sum problem is not known to imply one function. So they only have one-sided implication in this second black arrow. And now let us introduce our main theorem. So we showed that first, the average case hardness of MCKTP is equivalent to the existence of one function, and this problem MCKTP is also NP complete. So what is MCKTP? MCKTP is the minimal t-time bounded conditional Kolmogorov complexity problem, which we'll introduce very soon. Let me highlight here that for our results to hold, this problem has to be defined with respect to RAM machines as opposed to Turing machines. And we believe that RAM machines are equally motivated as Turing machine, if not more. So let us introduce the notion of Kolmogorov complexity. So we know that the notion of Kolmogorov complexity gives us a way to kind of estimate the amount of randomness in a fixed individual string. So for any string x, we let k of x denote the length of the shortest program that produces the string x. And to show that this K complexity is really something very hard to compute, let's look at this beautiful picture here. Well, it looks really complicated, so it would seem that it has high Kolmogorov complexity, but in fact, it could be generated by a small program of only a few lines. So therefore, it has like small K complexity. And we know that the notion of K complexity has a lot of amazing applications, but unfortunately, this notion is actually like too hard and it's uncomputable. So instead, we have to kind of twist the definition a little bit, and we consider time-bounded Kolmogorov complexity, and this which is also a classic notion. So in this notion, we add like a running time bound on the program that we want to run. So for any function t, we let k superscript t of x denote the length of the stratus program that produces the string x within a certain time bound, namely t of length of x. So now, by adding a running time bound, we know that this notion is computable. So the question is whether kt can be efficiently computed when t is a polynomial. And this is, again, not a new problem, and it has been studied in the Soviet Union since the 60s. And this problem is not known to be NP-complete. And in addition, we also consider the so-called a conditional variance of Kolmogorov complexity. So imagine that we still want to kind of find the shortest description of the string x, but we are given some auxiliary information for free. And imagine that we have an auxiliary string in the sky z, and it's free to get access to the string z. And we ask now what's the length of the smallest program that outputs x within a certain time bound, given the auxiliary input z. And we want to highlight here that the notion of program here has to be taken to be RAM machines. And by RAM machines, we mean those machines that have random access to its memory. So it's just like our modern computer, which really have a memory inside. And more formally, we will fix a universal RAM machine U to guarantee that our K complexity notion makes sense. We're looking for the length of the shortest RAM program pi, such that the program pi on input z, when simulated on the universal RAM machine U, will output the string x within time t of length of x. Now let us introduce the problem McKTP zeta that kind of appears in the main theorem. So there are two important parameters in this problem. So the first is the running time bound t, and the second parameter we call zeta is the length of the auxiliary string. So in this problem, we will consider auxiliary inputs of length zeta. So in more detail, this problem consists of a x, z, k, where the kt complexity of x conditional z is at most k, and length of z is zeta of length f of x, and k is, we can think of k is an integer from 1 to n. And so with this definition of this problem, let us also introduce what we mean by mild. This problem is mild average case hard. So we know that when we say some algorithm is a worst case algorithm, we really mean that it should work or it should succeed on every input x, z, k. And we also consider an average case heuristic for this problem, and we only require an average case heuristic to succeed on uniformly random input x, z, k with high probability. And we mentioned that this auxiliary input z should also be picked randomly. And now we can define the notion of average case hardness of McKTP. So which basically says no average case heuristic can decide this problem. And with high probability, we mean that there exists a polynomial p such that this PPT heuristic succeeds with probability 1 minus 1 or p of n. And we require that no such heuristics exist. So now let us introduce our main theorem. We showed that for any polynomial t that is n squared, there exists a polynomial zeta, such as first say the average case of McKTP is equivalent to the existence of one function, and this McKTP zeta problem is NP complete. So in some sense, we say that MKTP zeta is kind of an appropriate choice kind of sitting in this little picture. And we obtain a crispy characterization of the holy grail. Basing one function on NP is not equal to P is equivalent to proving a worst case to average case reduction for McKTP. And also the proof of our main theorem will shed some new light on the celebrated symmetry of information theorem. And let us introduce this theorem. So this theorem by Kolmogorov 11 states that for any string x and y, the k complexity of x concatenated with y is roughly the k complexity of y plus the k complexity of x given y within like a logarithmic range. So well, this is a very cute theorem about kind of information in a fixed string. It basically says that the information amount of information in x concatenated with y is roughly the amount of information in the first string plus the amount of information in the second string given the first string. And however, the proof involves exhaustive search, and the natural question here is whether a polynomial bounded version of this theorem holds. So, so this polynomial time bounded version of it would basically replace the k complexity here by its a polynomial time bounded version, namely kt. And we also kind of allow a small overhead in both sides of the inequality. So this gives these two inequalities here, which we refer to as a polynomial time bounded symmetry of information. And Kolmogorov suggested that this might be a good test case to prove that for some task, exhaustive search cannot be avoided. And by using the techniques in our main theorem, we showed that the length unrestricted version of polynomial time symmetry of information assertion is unconditionally false. So these two inequality unconditionally do not hold. I want to remark here that the length restricted here means that xy can be of different lengths. And this is also the case where the standard symmetry information considered. And now let me introduce some related work. There is a very beautiful line of research focusing on proving NP hardness of MCSP, minimal circuit size problem. And this problem is closely related to MKTP. And more importantly, specifically in Lango 20 showed the NP hardness of a conditional variant of MCSP. And our results showed NP hardness of McKTP. And I also want to mention a recent very elegant work by Allender, Shirashki, and Mayor. I'm sorry, Allender, Shirashi, Marish Otis, Tiramala, and Volkovich. So they first claimed that there is a NP complete language whose average case hardness implies the existence of one function. But very unfortunately, later there was a bug discovered in their first draft, and then they concurrently and independently considered a different conditional Kolmogorov complexity problem in their second draft. And in the third draft, they showed that the average case hardness of this problem is equivalent to one functions in NC0, and this is a pretty cute result. So let us briefly sketch how our main theorems are proved. So theorem 1, which is the one function theorem, closely follows from Liu and past 20, and I'm going to skip the proof of this theorem, and we refer to the full paper for more details in this proof. And we will briefly discuss how theorem 2, namely the NP completeness proof, is proved. So to prove this MCKTP is NP complete, a simple observation is that this problem is actually in NP. To see this, this basically follows from these parameters t and zeta are polynomials, and therefore this language can be easily shown that it is in NP. So now the starting point of our NP hardness proof, which follows Elango 19, is the result by Trevisan that approximate bounded set cover problem is NP complete. So let us introduce the bounded set cover problem. So an instance contains set S1 to Sr, which are subsets of the universe 1 to the n. And each set Si has a property that the size of the set Si is constant. So the goal of this problem is to find a minimal set collection of these sets, such that the union of the sets in this collection will give us the universe. So we call it, so it's just like a bounded, so it's just a set cover problem, but the size of each set is bounded by a constant. And please allow me to focus on a concrete example in this talk. So here the universe is just 1, 2, 3, and the set S1 contains 1, 3, S2, 2, 3, and the set S3 contains only 3. And here's like a little picture illustrating this concrete example. So first, let me replace these two pictures in different locations. And now the first step of our reduction is to play each element in the universe by a large random string. So we first replace 1 by a large random string, and we look at each set Si to S3. If it contains the element 1, then we put the same random string here. So if it does not contain the element 1, we put a bunch of zeros of the same length here. So we do the same for the element 2 and for the element 3. And we call the randomized version of the universe A, and call the randomized version of S1, S2, S3, W1, W2, W3. And we want to mention that we are not the first one who doing this, and this follows from Elango 19. And the second step of our reduction, in which we consider a very long string Z, and initially this is the all zero string, and then we'll put W1, W3 into random locations in this very long string Z. So for W1, we sample random location K1 and put W1 here. And we'll do the same for W2, put it in K2, W3, put it in the location K3. And now we ask, what is the length of the shortest RAM program, pi, such that pi on input the string D will produce the randomized version of the universe A, and pi runs in a time t of length of A. We want to remark here that D is so long such that the length of D is even larger than the running time bound of pi, namely t of length of A, so that for pi, pi could not even read every bit in this very long string Z. And we will show that if the size of the set cover in this for this instance is at most L, then the KT complexity of A conditional on Z is at most L times of log n. And on the other hand, the KT complexity of, if the KT complexity of the A conditional on Z is at most L times of log n, then the size of the set cover in this instance is at most O of L. So if these both statements are true, then we show that if we can decide MCKTP, then we can approximate the size of set cover in this instance, and therefore concludes our proof. And we remark here that the proof of these two statements are a bit complex, and we spent a significant amount of work in proving these two statements. So I don't have enough time, so I won't be able to cover these two proofs, and we refer to the full paper for more details. So now we conclude our main theorem. We showed that, say, well, McKTP is NP-complete and its average case hardness characterizes wave functions. So this is the first nature NP-complete language whose average case hardness characterizes the feasibility of basically tasks in crypto, including signature scheme, PRG, PRF, and commitment scheme, and so on. So we showed that, say, to achieve the holy grail of cryptography, we just need to, and we also have to, prove a worst case to average case reduction for this program, for this language McKTP. And our talk ends here. Thank you for your listening.